Here tonight, I'm Dr. Frank Summers from the Office of Public Outreach. All right, can we get the lights down and we'll ready to start? Hold on, check my microphone.
Mic check, mic check. It sounds beautiful. I get my voice right. All right, and one last, that was the one other question. Do we have enough lithographs? Hence, we have a rather large audience because Courtney is obviously famous. Do we need more lithographs? Do I need to go grab some at halftime? We seem to be okay. Or is somebody saying, yes, we need more? Okay, I'll get more. All right. All right, Thomas, let's get started. Good evening, ladies and gentlemen. I am Dr. Frank Summers from the Office of Public Outreach, and it is my pleasure to be your host for the public lecture series tonight. When you came in, there are images of the Jovian planets over here and over here. If you didn't get one, grab one on the way out. And if you don't know what Jovian planets are, well, you didn't pay attention in school, or they didn't use the term Jovian. But look on the back of the lithograph, and they will explain it all to you. Tonight, our speaker is Courtney McManus. This is one of the fun things, okay, that we get to do here. We get to tell you the inside story of what goes on behind the scenes of these amazing programs. So this is the view from mission operations. I know very little about it, so I'm looking forward to hearing all this talk. Let's see, next month, Nolan Walborn will be talking on active luminous blue variables in the Large Magellanic Cloud. And if you want to know what that means, show up. He sent me his abstract today, and it looks like it's a nice, juicy science topic talking about some very, very bright stars in a satellite galaxy. In October, we have another really special talk because the Cassini mission has been at Saturn for over a decade, gathering amazing images, and its grand finale is mid-September. I think it's like September 15th. All right, and so on October 3rd, Bonnie Meinke, our Saturn specialist here at Space Telescope, will be telling you all about Cassini's grand finale. And I don't know what she'll be talking about. She doesn't know what she'll be talking about because it hasn't happened yet. So she will be spending the last 2 weeks of September creating this amazing talk for you. Of course, there's always stuff that Cassini has done before. All right, November, we have the famous TBA, which means I need to get on email and start twisting people's arms. If you want to find out whose arm I do twist, you can check our public lecture series website. If you just go to your favorite search engine, type in Hubble Public Talks, you will find this web page where we have the list of the upcoming lectures. We have the links to watch the live streams on the first Tuesday of every month, as well as the list for the archives of the past lectures. Also, if you would like to sign up for our mailing list, this is the easiest way to do so. Just enter your email here, hit that subscribe button, and it will sign you up for our emails. The announcements, if you don't want to sign up at the website, you can just provide your email address to me. Somebody already did that this evening, and I will do my best to get you on there, okay? And I think we've got a perfect record of no spam ever on that email list. If you have comments or questions, you can also send them to us at publiclecture@stsci.edu. Social media. I updated this because we've got a new push on the social media. You know, we've been known as the home of Hubble, right? But what's happening next year? The James Webb Space Telescope is launching. So we aren't just the Hubble place, we're also going to be the James Webb place. And, well, we're really the Space Telescope Science Institute. So our social media is expanding from just Hubble to also including STSCI. So on Facebook, we have Hubble Telescope. We also have our STSCI page on Facebook. Twitter has Hubble Telescope as well as Space Telescope. YouTube, we just have Hubble Site Channel. And on Instagram, we have Space Telescopes. So I think you'll see our branding grow beyond just being Hubble and Webb and being Space Telescopes over the next couple of years. So that's something to look forward to. For myself, you can follow me on Facebook, Google+, or Twitter. I don't do a heck of a lot of it, so it's not the most exciting, not a very, very full feed. How about that? Okay. Observatory. I did not get an email, but it was raining at 6 p.m. Did it clear up since then? You guys coming in? Somebody saying yes? Okay, a little bit. All right, so we're not sure whether there will be observing, but that person will show up around 9:15 and remind me at the end of the talk to ask if Irini is here, okay? Okay, and now our news from the universe for August 2017. Our first story tonight, giant arc reveals tiny details. All right, so we're talking about gravitational lensing, and actually we've had a lot of stories lately about gravitational lensing. This is gravitational lensing by a cluster of galaxies, and so the configuration is Hubble's down here, we've got this giant cluster of galaxies here, and we've got this very distant galaxy here. And the light from that very distant galaxy passes by this large cluster, and due to an effect of general relativity, actually gets bent. Because general relativity, as everybody in the back of the room knows, can be boiled down to 3 words. Mass warps space. Okay? That's what you need to know about general relativity. And the mass of this cluster warps space so much that the light bends as it goes past that cluster. So the cluster of galaxies, the mass of the cluster of galaxies, acts as a gravitational lens. All right? And so when Hubble looks at these big clusters of galaxies, we can get lensing effects like this, which is an arc. And this is a distant galaxy whose light has passed through that cluster and becomes stretched out as it passes through. All right? And so this one is actually a very big arc. There are actually a lot of smaller arcs like that one here, and there are a couple other smaller arcs that you can see in this image. But this is a giant arc, and there was a survey by the Sloan Digital Sky, going through the Sloan Digital Sky Survey to look for these giant arcs in Sloan, which is a ground-based telescope, and then do follow-up with the Hubble Space Telescope. And so we did follow up with Hubble of this one, all right, and let me blow it up for you. And this giant arc is not well, it is one galaxy, but it's the same galaxy 3 different times. It's a triple lens of the same galaxy. So you can see one image of it here, one image of it in the center, and one image of it down here. And that's one of the reasons it makes for this really long arc, okay? And this galaxy is observed from 11 billion light years away, right? And we could not really see it very well at all if it wasn't for the cluster of galaxies lensing it. It's magnified about 30 times. It's brightened up. It's also expanded. So what they did with this is they used their model of the mass of the cluster of galaxies to try and reconstruct what this galaxy originally looked like before it went through the lensing, because it's distorted a little bit. All right? And so they reconstructed what they think this galaxy actually looks like before it gets distorted by the gravitational lensing. And what they measured was that due to the gravitational lensing, they're able to get about 10 times the resolution that Hubble would get normally. All right? With the lensing, it's stretched out, magnified enough, they're able to see finer details than Hubble could without the gravitational lensing. As I said, this galaxy is 11 billion light years away, which means we're seeing it as it was 11 billion years ago. Because it takes 1 billion years to cross 1 billion light years of space. This is a galaxy seen 11 billion years ago when galaxies were still developing. And at that time, these small galaxies were undergoing massive bursts of star formation. And you can see in the reconstruction all these bright small dots. Right? That is the star formation regions bursting to life 11 billion years ago. And we have known from other observations that we get a lot of star formation. We get these star bursts early on in the universe. But with this, we're able to see them in unprecedented detail because it's even higher resolution than Hubble can get due to the lensing. We're able to see these small star-forming regions that are only hundreds of light years across, whereas normally Hubble would only be able to see things thousands of light years across, and all the star bursting would be blurred together. Now we're able to see that individual star bursting in this galaxy due to the giant arc helping us to resolve very tiny details in this very distant galaxy. That's really cool. Oh, and by the way, this is an artist's illustration of what's going on. This is the galaxy seen mostly edge on, and you got all these wonderful star-bursting things going on. All right, we like to add the pretty pictures because, well, that's only so pretty. And this gives you an idea to help your imagination look what it might have looked like 11 billion years ago. Question?
Just the view.
That's the view of the galaxy. The galaxy is not destroyed. Only the light is destroyed. No galaxies were harmed in the creation of that image, okay? Our second story, a Phobos photobomb. All right, so Mars and Earth go through what's called opposition every 26 months, I think it is, every 2 years and 2 months, okay? And this is a diagram showing you all the some of the opposition pictures Hubble has taken. So whenever Earth and Mars are at their closest, Hubble takes a picture and we put it out there and the public loves it, okay? Because, sorry, the public loves solar system pictures. So we did one in 1995 and in 97 and 99 and 2001 and 2003, 2005 and 2007. Okay, so this was, you know, a procession of all these various oppositions. So we've continued to do that over the years. And last year in 2016 in May, we also took a picture of Mars getting close to opposition. And what we showed you about it this time, because we've done this so many times, we got to talk about new things each time. Well, this time we talked about all the different features on the surface of Mars that Hubble could resolve. The clouds above Syrtis Major, Schiaparelli crater, the North Pole, and so on and so forth. But we didn't tell you, what we didn't tell you was during those observations, we took a bunch of observations, Mars's moon Phobos appeared in 13 of those observations. All right, and for those of you on the web, you may not be able to see those dots, so I'm going to circle them. All right, this is a composite of 13 observations, including Phobos being along here. All right, so they actually timed it to try and see what they could see about this tiny moon, because this is only, you know, tens of kilometers across. This is a captured asteroid, actually. Okay, it's not a moon that formed with Mars. It's a moon that got captured by Mars. Both Phobos and Deimos are these tiny moons around Mars that are really almost assuredly captured asteroids. All right, and so here is the data sequence. All right, and you can see Phobos moving here. You'll also see Mars flipping through it because we got different observations during different Hubble orbits. All right, and so Mars goes through. And this is the actual data, okay? But if you want to make a movie, this kind of jumpiness doesn't work. So what we did is we had our video guy apply his special magic to it, and now we have a smooth sequence that shows Phobos progressing through those 13 different sequences, and you'll notice Mars here turns relatively smoothly as well. All right, and we didn't come up with this name. Actually, Goddard Space Flight Center used the phrase Phobos photobombing, and it caught on really well on the internet. And so I picked it up. I said, all right, that's a cool name. So this is Phobos photobombing our picture of Mars. All right. Final thing, where will you be when the light goes out? I have to, we've been waiting for this for how long? All right, it's finally 2017. It's finally August 2017, and the total solar eclipse that goes across America will come on August 21st. So Monday, August 21st, there will be if you haven't paid any attention for the past 5 years, there will be a total solar eclipse that starts around 10:15 a.m. out in Oregon and passes through South Carolina somewhere around, 3 p.m., okay? And if you're in the path of totality, you will see the total solar eclipse. However, if you are anywhere within North America, you're pretty much going to get a 60, 70, 80, 90% eclipse, okay? There are lots of tools out there on the web. I don't need to go through them. We gave a complete talk on January. Go back and watch that talk, and you'll have all the details if you want. There are if you are not in the path of if you're in the path of totality, there are these tools that will tell you, when it starts, when it's maximum, when it ends. All right, and so in Salem, Oregon, they're going to have a 1 minute and 55-second total solar eclipse. If you stay here in Baltimore, you will have not a total solar eclipse. You'll have a partial eclipse, about 80% obscured, and its maximum will be at 2:43 in the afternoon. Okay, lots and lots of cool tools out there, lots and lots of cool websites. I advise you to take advantage of them beforehand. All right, the one thing that I always have to say for every audience is protect your eyes. Okay, do not use sunglasses. Do not use a Mylar balloon. Do not lose something your Uncle George told you, oh, this is safe, right? No, you want certified solar viewing glasses, okay? They must be certified to protect your eyes. All right, I was down at the beach this weekend talking with somebody about it. I said, take a look at the sun right now. How long can you look at that before it starts to hurt your eyes? Okay? This is what you need to do. If you want to stare at the sun and watch that total solar eclipse or partial eclipse, you need something that really blocks the light so that you don't hurt your eyes. And after he stared at the sun for about 4 seconds, he got the picture. Oh, yeah, okay. Kept seeing the sun for about 30 seconds afterwards, right? So you want eclipse shades, okay? Whenever any part of the sun is visible, you want to be wearing them. If you happen to get into totality and during the few minutes of totality, then you can take them off and look at the corona. And actually, I'd suggest you do, because you keep them on during totality, you're not going to see much. All right, you'll need to take them off during totality. But once totality stops, put them back on. Okay, protect your eyes. They're available online at lots of different places, and they're only a couple bucks. Yes.
I did a little research just the other day. Most of the sites are sold out.
A lot of the sites are sold out. Okay, so it's too late. Forget it. You're done. Wait until 2024, because we're going to have another total solar eclipse through America in 2024. This doesn't go coast to coast. It comes up through Mexico, goes across Cleveland, and out through Nova Scotia, I believe. So, all right, so if you didn't buy them now, buy them next year, because you need them, and you'll need them again in 7 years. Okay? Yes.
I saw a total eclipse when I was a kid, and they did something simple, like you took a piece of paper, you poked a hole in it.
Right. So if you don't,
you could actually see the.
Right. Thank you for reminding me, because I was going to mention that. If you don't have eclipse glasses, you can use a pinhole camera and project the image of it onto a piece of white paper. Okay, and that works extremely well too. I remember I was up in Massachusetts when I was a kid, and we did pinhole cameras. We didn't have eclipse glasses. Way back when I was young, they didn't have those fancy, I certainly didn't know about them when I was a kid. But yes, you can use pinhole projectors, and there are other ways to project the image. Again, lots of websites out there. Take advantage of it just to take care of your eyes. All right, so that is our news. And now we go to our featured speaker tonight. As I said, I'm excited to hear this. Courtney McManus is an expert at things that you don't see, except for in movies, I guess, in mission control. She got her degree in aeronautical and astronautical engineering from Purdue. And then she went to one of the most famous places of all, Johnson Space Center. Worked in mission control a little bit on the shuttle program, but mostly on the International Space Station. We are very lucky we stole her, got her to come here 3 years ago, where she is in a title that I can't remember. Systems Integration and Test Engineer. See, I knew I'd remember it. One of the things I'm sure she'll tell you is that we have the Missions Operations Center for the James Webb Space Telescope upstairs. And so JWST will be run from here. Hubble is being run from Goddard Space Flight Center. So people like Courtney are incredibly important for our future missions. And for Courtney, that gentleman right there is important for her future mission, because she tells me she's getting married in 1 month. Okay? So, ladies and gentlemen, while she's still single, let's hear for Courtney McManus.
Hi, everybody. Can you hear me okay? One, I mean. There you go. Let me just log into my computer. Hold on. Haha, success. All right, so as Frank said, my name is Courtney McManus, and I'm here to talk to you about what it takes to make space missions happen, kind of the stuff behind the scenes. So before I go into anything, has anyone here seen the movie Apollo 13? Raise your hand. Excellent. This will make it much easier for you guys to have a frame of reference. If you haven't, don't worry. I'll guide you along. Hi, my name's Courtney, like I said. If you have any questions at any point, feel free to ask. Otherwise, hold them to the end, and we'll take them then. I have a secret for you guys. I'm not an astronomer, so you guys might know more about astronomy stuff than I do, having come to these lectures a lot. The topic for the talk next month, the blue variable stuff, I don't really know any of that. I know what a photon is, for the most part, and I know what it takes to make all of the stuff the astronomers want happen, but I am not an astronomer at all. Right now, I am a systems integration and test engineer for the James Webb Space Telescope. So you guys probably know the James Webb Space Telescope's in development right now. Parts of it are down in Houston, parts of it are out in California. The Mission Operations Center is being developed and designed here. My job as a test engineer is basically to take stuff that people work really, really hard on and try to break it. And I hope that I don't break it because they've usually done their job really well. But sometimes we catch little errors that might happen, and we try to do that before it gets into space so that we can fix everything before it goes up there. So that's what I do right now. But I'm going to talk to you about what I used to do when I was a flight controller with the International Space Station down in Houston. This is actually a picture of me. That's me, that blur right there. Working on console and mission control. This was on NASA television. My mom took this screenshot to prove to my grandmother that I was in there. It really could be anybody, but that's definitely me. And here's a picture of me really excited next to a Soyuz capsule, which is what the Russians use to send cosmonauts into space, and we also hitch rides on there every now and then to send astronauts up into space too. So I got to be next to one. It was really cool. So I'm going to talk to you about my time working as a flight controller with the ISS. This is the ISS. This is ISIS. It is not the ISS. This is the ISS. Sometimes people get confused when I talk quickly. It sounds like I'm saying one thing, but I'm talking about the ISS. So the International Space Station, or the ISS, is orbiting up in space about 400-ish miles up there. It kind of fluctuates a little bit. Right now we have 6 people, I think, on board the ISS. I definitely should check that before I started talking. But usually there's a crew of 6 people from various countries up on the ISS working and living in space all the time, doing science experiments, learning how our bodies adapt to space, making it so we can do longer-term spaceflight missions out to Mars, etc. So does anyone know where mission control for the ISS is? Shout it out if you know. I heard it. Houston, yes, you probably have heard the line, Houston, we have a problem. That's because they were talking to Houston, not just like some guy named Houston, it was the actual city. So this is the very beautiful building where the Mission Control Center in Houston is located. It's called the Christopher C. Kraft Jr. Mission Control Center, named after Chris Kraft, his name's actually Christopher Columbus Kraft, which is, I don't know if I'd want that name, but it's named after him. He's one of the founders of mission control. There's a whole theory out there that he helped to develop on what it takes to be a really solid mission control flight director and flight controller. Some really interesting stuff out there on him if you're interested in more detail after I finish my talk. I suggest looking up Chris Kraft. Anyway, so this is a beautiful building. There are no windows. When you're inside, it's very dark and very cold. I was always freezing in mission control, but it's actually better that there are no windows because then you can't tell that it's 3 in the morning and you're sitting at work. because the Mission Control Center is staffed 24/7, 365. There's a person who has to sit in there on Thanksgiving and work at 3 in the morning. But usually people are nice and bring them food. There's always food in Mission Control. A fun fact about this building is anytime you see a flag flying out on the top, it means there is someone in space. It used to make more sense during times when we just had the shuttle flying, because the shuttle wasn't up there all the time. It would happen intermittently, so you can look and say, oh, there's a shuttle mission, cool, someone's up there. But now it's always flying because there's always someone manning the International Space Station. So once you go inside that building, there are these really fancy looking doors that it's really hard to get through unless you're authorized. So don't ever try. It's really tough. There's lots of sirens and guards and such. But once you get through those doors, you go through some catacombs a little ways, and then you get to this room here. In the Mission Control building, there are a handful of different Mission Control centers. This one is for it's the flight control room for the International Space Station. And I'm going to talk to you about what all of this is, who all these people are, what they do, what it means, stuff like that. But first, I want to show you a little intro video to get your head in the right space for what Mission Control is. I thought about showing a clip from Apollo 13, and then I realized that there's like actual stuff that happened and was filmed, so it'd be way better if I showed you a clip from an actual Apollo mission. It's way better than Apollo 13. So in this video, this is a really excellent video of a small snippet of when they were landing the Apollo 11 lander. In this video, you'll see Gene Kranz, the flight director, and you'll see a handful of other mission control people that are in there. You'll also see, oh gosh, I don't remember what his name is, but you'll see the Capcom, or the capsule communicator, who's the person who's talking to the capsule up in space. You'll hear two different voice loops, is what they're called in this film. You'll hear what's called the flight loop, which is how the flight director talks to all the other flight controllers, and you'll also hear the loop on which the capsule communicator talked to the spacecraft. So you'll hear both of them. So you're going to hear them go through a sequence of the flight director polling all of the flight controllers as to whether or not the systems and the people are ready for the actual moon landing. So I hope this works. It's going to be really cool.
Okay, all flight controllers, go, no go for landing. Retro.
Go.
Fido.
Go.
Guidance.
Go.
Control.
Go.
Telcom.
Go.
GNC.
Go.
Econ.
Go.
Surgeon.
Go.
Capcom, we're go for landing.
Eagle, Houston, you're a go for landing, over. Roger, understand, go for landing, 3,000 feet. Copy. Alarm.
Oh no, you know what's happening? You're only hearing one of the feeds.
1201. 1201.
You're supposed to be
Roger,
two.
1201 alarm.
Same type, we're go, flight.
Okay, we're go.
We're go, same type, we're go.
Flight Fido right on, real good.
2,000 feet, 2,000 feet, into the ag, 47 degrees. Roger.
It's less
How's
How's our
direct
margin looking, Bob?
when you only hear
It
half
looks
of
okay. We're about 4.5. Roger.
All right, well, so the way they have the video set up is so that in the left audio channel you hear one, and in the right audio channel you hear the other, so it must have not been both channels coming through. But that's totally fine. You guys heard at least the flight director loop, which was pretty cool. But you could hear, I suggest go look it up after this talk, not during it probably, but after the talk. Oh gosh, sorry. Excuse me. I lost my train of thought because I was going to talk about the two audio channels, and then there's only one. So when the Apollo 11 lander was landing on the moon, there was an alarm that sounded on the spacecraft, and you can, in that, it's called the 1201 alarm. In that video clip, in the audio, you could hear the astronauts calling out the 1201 alarm, and then you can hear the flight controllers talking amongst themselves, saying, oh, it's an alarm we've seen before, everything's fine, we're still go flight, and then flight tells the Capcom to tell the crew that they're still go to land, and then the crew can still go to land, and then the crew lands, and you all know what happens after that. So that kind of puts into perspective a little bit of what has to happen in mission control to get things to go on. So now I want to orient you a little bit to the flight control room of the International Space Station. So the flight director sits right here in the middle of the room, and the Capcom is right next to him or her. But up here, we have a couple of different pretty nifty things that I want to point out to you guys. We have this thing right here in the middle called the bird's eye view, which is a map of the world that shows where the ISS is at any point in time. It's kind of hard sitting on the ground to visualize where in space it might be, so they just throw it up in the middle so everyone knows. It also shows, now you can't see it very well in this picture, but it also shows the dark and the light, so it shows when the ISS is going into eclipse and when it's going to be in insolation or in sunshine. It shows where some of the communications satellites are, so we know which satellite the ISS is talking to at any given time. It also can show things like the attitude and orientation of the ISS right here, which is important when you're thinking about where your antennas are pointing, or if you want to take an observation of a certain point on Earth, or you want the astronauts to go take a picture of a volcano erupting, you need to know which window to go look out of. Then you have camera feeds coming from either inside or outside the ISS on these three screens here. And on this one here, and kind of on the right-hand side, is the caution and warning screen. So at any time, there might be a handful of things that aren't going the way they're supposed to on the different systems in the ISS, and the various flight controllers need to be aware of it. They're all aware of it in some degree for their own systems, but you might need to know something about another system. So that's thrown up here. It's actually not great that there's red and yellow right here because that means something not good is happening. So I don't know when this picture was taken, but it's not good. It's not good to see red in mission control, just as a general rule. So let's see. This was the video I showed you. So we'll switch back to this picture here. So I want to jump in and I want to talk to you guys about what each one of these console positions do. And then at the end of talking about ISS, I'll jump in a little bit to what the different consoles and experts will be for the James Webb Space Telescope. So first I want to talk about the flight director and Capcom. That's who you guys saw in the video. It's who you might be most familiar with from the movie Apollo 13, things like that. So the flight director is totally in charge of everything ever on the ISS, period. There are a handful of mission control centers. I forgot to mention that. There's a mission control center in Moscow. There's a mission control center in Germany. There's one in Japan. There's one in Houston. There's actually a payload control center in Alabama. So there's a handful of different control centers all over the place. And each one of those control centers has their own flight director. But the flight director who's in Houston is the #1 person in charge. He or she makes the final call on everything that happens on the ISS. So you may recognize Ed Harris from the movie Apollo 13. He was the flight director playing this guy, Gene Kranz, who you saw from the video before. Gene Kranz is a really cool guy. If you haven't heard about him before, definitely look him up. I saw him once on an airplane and I got really excited flying back to Houston. It was very cool for me. But it was cool on the outside, like, oh, hey, how's it going? But on the inside, I was like, oh my God, that's Gene Kranz, that's so cool. So the flight director, like I said, is in charge of everything. So he or she is the person in the room who has final say. Even if the president called and wanted something to happen on the ISS, it couldn't happen unless the flight director said, yes, it can happen. So kind of give you an idea. So Capcom is the capsule communicator. Probably the most famous Capcom you guys have ever heard of is the actor commonly known as, oh yeah, that guy, whose name I don't actually remember. Gary, that's right. So he played the Capcom in the movie Apollo 13. But a real-life Capcom can be seen here. This gentleman right here is the current Capcom, not current like now, but current when the picture was taken. This is the current Capcom and the flight director sitting in mission control. The Capcom and the flight director always sit next to each other. And the Capcom is, for the most part, the only person that can talk to the astronauts in space. This was especially important in Apollo, Gemini, and the space shuttle. It's a little less important now at the ISS since we have people up there all the time working on different experiments and stuff like that. You want different specialists to be able to talk to them. But anytime there's a dynamic operation happening, and especially in the days of the shuttle, Capcom was the only person who could talk to the astronauts. Capcom was generally a former astronaut themselves, and the reason that this is so there is only one voice that the astronauts hear, and they're not hearing all of the craziness that's happening on the ground. And the reason it's a former astronaut is because they generally know, in this situation that's happening, these are the things that I would want to know up in space, and these are the things I need to hear in order to react to the situation. So now it's not just astronauts, but different specialists and stuff who can talk to the astronauts and acting as Capcom. Anastasia.
How did they do that?
Yeah, so there is a flight director office. If you didn't hear the question, it is what happens with 24/7 coverage? Are there multiple? Is there a deputy? That sort of thing. So there's a flight director office that has, I don't know how many, but a whole cadre of flight directors. So the on-console flight director is the person who has the final authority, the person who's in the room at the time. There's also, for every increment on the ISS, that's when a new crew of 3 people flies up on the Soyuz. That new group of 3 people is called an increment. So for every increment, there's a lead flight director. And they're kind of the ones who oversee the activities from start to finish of the increment. But with 24/7 ops, the flight director console is one of the consoles that's staffed all the time. There's always a flight director. There's not always a Capcom, like when the astronauts are sleeping. Because even though they're in space, we still let them sleep 8 hours a day. In fact, it's planned into their day. They have to sleep 8 hours. They even get free time. If they want free time, they do that. Sometimes you get an astronaut like Peggy Whitson, who recently broke a record for most days in space. She's so cool. In her free time, she would just do more stuff. Like, it's called a task list that they have for the astronauts to do while they're on orbit. So if they have a little bit of free time and maybe want to advance science or something, they could do that. Peggy Whitson worked through the whole task list, and we had to pull stuff from other task lists just to give her because she was so cool. It's awesome. I saw her in an elevator once too. It was really exciting. Anyway, so the Capcom console is not staffed when the astronauts are asleep, or maybe at some other times, but the flight director console is always staffed. So that brings me into the other consoles that are staffed 24/7, 365. Or 366. We also staff on leap years. So we've got ADCO, Kronos, Ethos, and Spartan. You should pay attention because there's going to be a quiz. And I'm going to talk about what each one of these do. It won't surprise you to find out that each one of these names are acronyms because at NASA, everyone loves acronyms, even though some of them are a stretch. And I'll show you in a second. So ADCO is the Attitude, Determination, and Control Officer. They are the people who determine and control the attitude for the International Space Station, as you might guess. So what does that mean? Much like an airplane can go this way and this way and this way, the space station can also go this way and this way and this way, but it also goes this way around the Earth. So the ADCO is the console in charge of making sure we know how the spacecraft is oriented and where they are in over Earth orbit. You can think of them as kind of the ones who actually fly the ISS. And that's what they'll tell you if you ever talk to an ADCO, is that they're the ones who fly the ISS. So we also have Cronus. And this is an example of one of the acronyms that's a little bit of a stretch. They're the Communications RF Onboard Networks Utilization Specialist, obviously. And they utilize communications and RF onboard networks? No. They are in charge of the communication between the spacecraft and the ground. They're in charge of the video feed from the spacecraft on the ground on the outside and the inside, and they are in charge of the computers. Now this is a little bit of a misleading picture because they're not in charge of the computers such as laptops and stuff. They're in charge of the computers that the ISS uses to talk to itself. So all of the commands that we send up to the spacecraft get processed through computers and sent to the different subsystems. Like if you want to turn on a fan in one module, you'd send up a command to turn on that fan. The computers that Kronos is in charge of is what takes that command, understands it and sends it to that fan to turn the fan on. So that's how they utilize communications, RF onboard, and networks. Next we have Ethos. Ethos is the Environmental and Thermal Operations System Specialist. They are the ones in charge of life support and climate control. So they are in charge of basically the health and safety of the astronauts and making the International Space Station a livable place for us to send people. They are in charge of ventilation, not with a fan like this, but with more fancy fans, space fans, if you will, that are in the ducts for the space station. Because if you think about it, in space, there's no gravity, right? Here on Earth, if you have a pocket of hot air, it rises, right? Yes, hot air rises. So if you have a pocket of hot air, it rises, and the cool air sinks. But in space, there isn't gravity to make those gradients happen. So you can end up with kind of just a pocket of stagnant air, just kind of there, and it could smell bad or have a concentration of CO2 in it or something like that. So ventilation on the space station is really important. You want to keep the air moving around so you don't end up with that stagnant pocket of air. They're also in charge of humidity control because, again, there is no gravity. So things don't condense out of the air and fall to the ground. It condenses out of the air and just kind of sticks to stuff. And you don't want that to happen, so you want to keep really good control over the humidity in the spacecraft. Also the temperature. Space is cold, so they don't want the astronauts to be cold, basically. So they keep control of the temperature on board the spacecraft, too. The Ethos specialist is also in charge of emergencies on the spacecraft. Can anyone think of an emergency on a spacecraft? Hint. Fire, yeah. So on board the ISS, there are 3 types of what you call an onboard emergency. There are lots and lots of things that could go wrong, but there are 3 things that will cause everybody to stop what they're doing and take care of the emergency. One of them is fire. Can anyone think of another one?
Leaks.
Yeah, a leak or a rapid depressurization. So if a micrometeoroid hits something and it starts to depressurize, that's really bad. We have to take all of the air up there, and we don't want to let it just go out into space. So a rapid depressurization or a leak is another one. The third one is kind of strange. The third one is an ammonia leak. Yeah, there is one very, very not likely path through which ammonia could be introduced into the atmosphere of the space station. It's never happened. It probably will never happen, but someone realized one day that through a series of very unfortunate events, it could happen. So there are a lot of detections in place and a lot of different signs that the Ethos looks for to make sure that ammonia doesn't get introduced into the atmosphere. Because ammonia is really bad, if you weren't sure. Yeah?
How is it that the oxygen doesn't run out in the space station?
That's an excellent question. The oxygen doesn't run out. The question was, how is it that the oxygen doesn't run out in the space station? That is also something that the Ethos specialist is in charge of. So on board we have regenerative life support systems. So we can take the water and turn it into oxygen and hydrogen. And we can even take like pee and turn it into drinkable water. So if you're not into that, don't be an astronaut. But I hear that it tastes just like water, and you would never know. We also, when the shuttle was flying, we also used to take big tanks of oxygen up to the space station to refill it that way. But the shuttle's not flying anymore, so I'm not sure if any of the other spacecraft do that, but that's a good question. I'll have to look into that. Yeah?
Do they also cover when astronauts get sick?
No, they don't cover when astronauts get sick, but I will tell you in a few slides who does. Yes?
What sort of fire protection systems do they have on board there?
So the question was, what sort of fire protection systems do they have on board? They have a lot of different fire protection systems on board because fire is probably the #1 thing they're very most worried about. There are everything from, you don't really want to loose a fire extinguisher in the space station because all those particles will just kind of float away. They won't necessarily stay right at the fire. So it's everything from like you can smother it with blankets, they have special fire blankets, to even closing off the hatch and venting out a module to get rid of all the oxygen so the fire dies. So there's a lot of different ways, depending on the severity of the fire and the location of the fire, what the approach would be. And all of the procedures for this are in a big notebook about this big, also probably on the computer, but there are hard copies backed up right behind all of the flight controllers. They can grab the emergency notebook and say, okay, this is what we do next. So it's very likely that most of the scenarios have been thought through, and they're able to combat the fire the way that they need to in order to keep the crew and the vehicle healthy. Yes?
Does Kronos have control over all ISS uplink and downlink? So say Capcom wants to transmit something to the astronauts that they get from Ethos. Does it have to go through Kronos first?
That's a good question. So the question was, does all of the uplink and downlink go through Kronos? Kronos is the person that owns the systems that allow the uplink and downlink to happen. But they don't have to talk to Kronos first before they talk to the astronauts. It's not the only way you can talk to the astronauts, though. There's also a ham radio on the space station that the astronauts use sometimes. So when it's flying over, if any of the astronauts are on the ham radio, you can talk to them that way. Fun fact. But Kronos is just in charge of the systems that allow it to happen.
Okay, so Kronos doesn't directly authorize communication.
Correct. Kronos just enables communication to happen. So the next console position that's staffed 24/7 is called Spartan, Station Power, Articulation, Thermal, and Analysis. It's another stretch kind of acronym name, but I think it's pretty cool. My parents went to Michigan State, so I like the console name Spartan. So Spartan is in charge of the electrical power on board the space station and the external thermal, excuse me, on the space station. You guys probably know that the space station is powered from solar energy. So Spartan is the console that's in charge of making sure the solar rays are pointed at the sun so that we're getting the most power we can out of the solar rays. They're also in charge of routing that power from the solar rays to the various components that need it. Yeah?
When you were talking about ADCO, you said they're in charge of basically how the space station is in relation to what, though? So it's up in relation to what? Or it's down?
That's an excellent question. So she asked how ADCO is in charge of how the space station is oriented, but oriented in terms of what? There's actually different attitudes at which the space station can fly, but for the most part, the space station flies like an airplane would around the world. So it has a forward, it has thank you, it has an aft, it has a port, it has a starboard, but it also has what's called a zenith, which is up, so away from the Earth, and a nadir, which is down towards the Earth. And it flies around at about 4 degrees of pitch every minute, I think. So it just kind of constantly pitches nose over so that it can fly around the Earth. There's other orientations. Once upon a time, there was a solar array that broke, and we weren't getting as much power as we needed to. So instead of flying like this, we kind of took the solar arrays and flew like this. So instead of around the Earth like this, we kind of just like went around the Earth like this. So there's different attitudes you can fly at, and it's always, though, determined pretty much Earth relative how you're flying. Does that answer your question? Cool. All right, I'm going to move on because there's lots of positions. Save your question for the end. There's lots of positions. I want to make sure I get to all of them and then talk a little bit about James Webb. The articulation in Spartan is the articulation of the solar arrays. Yeah, how the solar arrays are pointed. So they can articulate like this, and also like this. There's lots of exercises you could do as a space station flight controller to talk about your job. Okay, so those are the positions that are staffed 24/7, 365. There are 4 consoles that are staffed for what's called dynamic operations. Those are operations that aren't usual on the space station. So it's something like the docking of a spacecraft or a spacewalk, or the undocking of a spacecraft, or a robotics operation, something like that. So we have EVA, Robo, VVO, and ICE. I'm going to talk about each one of those now. First, we'll start with EVA. EVA stands for extravehicular activity. They are the people who are in charge of the spacewalks. So anytime an astronaut or a cosmonaut goes outside of the space station, the EVA people are in charge what happens. They are also in charge of training the astronauts. You guys may have seen pictures of, it's called the Neutral Buoyancy Lab down in Houston. It's this giant swimming pool that has the mock-up of a space station in it. It's where the astronauts can go practice being essentially weightless, to practice all the spacewalks they're going to do in space on Earth before they go into space. So that's the EVA console. They're on dock when EVAs happen. We also have the robotics officer, or robo. They are in charge of the different robotics operations on board the space station, most notably the space station robotic arm. And I'll talk a little bit more about the robotic arm in a second. We also have the visiting vehicle officer, who is in charge of the following spacecraft. The Soyuz, which is the Russian spacecraft that brings people up to the space station. The ATV, which is the European Space Agency's cargo resupply vehicle. And the Progress, which is the Russian Space Agency's cargo resupply vehicle. Fun fact, the Soyuz and the Progress are almost identical, except this one says Soyuz and this one says Progress, if you can read Russian. If you can't read Russian, the Soyuz has a periscope on it for the astronauts and cosmonauts to be able to see out of, because cargo doesn't need to see, but the astronauts do. So this one has a periscope. This one also has a crew cabin right here that's pressurized. This isn't pressurized, because again, cargo. We don't care. I mean, we care, we need it, don't get me wrong, but not as much as we care about crew. So then we have the Integration Systems Engineer, or ICE. They are in charge of the vehicles that come to the space station that are the Japanese HTV, the Cygnus, the Orbital's Cygnus vehicle, and SpaceX's Dragon vehicle. Can anyone spot a difference between the vehicles VVO is in charge of and the vehicles that ICE is in charge of, just from these pictures? What? Yeah, so that is one difference. These are commercial vehicles here. What about, there's something in these pictures that's not in these pictures. Yeah, so the spacecraft don't have the arms. That's actually the space station's robotic arm. These vehicles here, the Soyuz, Progress, and ATV, dynamically dock to the space station. So they actually fly in and autonomously, or are piloted, dock to the space station. These vehicles here, we reach out and grab them with the robotic arm and then carefully bring them in to berth to the space station. That's the difference between docking and berthing. Who knew? That's what I learned. So ICE is in charge of those vehicles that berth, and VVO is in charge of the vehicles that dynamically dock to the space station. Yeah?
Is that the same arm that the robotics officer?
It is the same arm that the robotics officer is in charge of. Oh, that's why I said I was going to talk about it again. That's good. So the robotics officer works with ICE to capture these vehicles. So ICE is the systems expert on the vehicles, and they work closely with Robo to reach out, capture the vehicles, and berth them to the space station.
They berth in the same docks that the directly docking would do.
Actually, they don't. These ones all dock to the Russian side of the space station, and these all dock to the European, Japanese, and American side of the space station. The space station's kind of like two space stations stuck together. That's not the official NASA terminology, but it's my official terminology. You've got the Russian side and the US side, and they're kind of just stuck together. And then on the US side, we also have a European module and a Japanese module and a handful of other things. But international cooperation, it's a really good thing. We just kind of stick them together. Well, I'll talk a little bit more about that in a second. So we have, these are the dynamic operations console positions. So we also have 4 consoles that support daily stuff. I didn't think of a better term for it, so I called it daily stuff. So we have Ops Plan, ISO, OSO, and Pluto. Yeah, we'll get there. So Ops Plan is the operations planner. The space station is a very, 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 very complex thing. There's all sorts of systems that have to operate in conjunction with each other. There are people that have to be scheduled throughout the day. Astronauts have to do things like eat and sleep and stuff. Ops Plan is the console that's in charge of making the schedule for everything. This is a screenshot of a thing called OSTPV, because we can't just call it the schedule when we could call it OSTPV. It stands for the Onboard Short-Term Plan Viewer, and it is literally everything that's happening on the ISS at any given time. So time goes this way, and then these different bands are, I don't know why I'm pointing when I have a laser. These different bands are the crew here, so this is the commander. All of his activities or her activities are here. This is when the ISS is in eclipse or in insolation. This is when we have different communications contacts. Literally everything on the ISS is on OSTPV. Ops plan is the person who takes all of that information, not the person, the console, it's not just one guy, but they take all of that information and they condense it into this plan that everybody follows. Here's a picture of a real live astronaut using it. Ooh. Has anyone seen the movie Gravity? So in the movie Gravity, not to spoil anything, but there's a scene that takes place inside the space station, and if you look at the computers, it has OSTPV on it. All right, I think that's really cool. I got really excited and was like, oh, look at the screen. And no one cared. So, okay, next we have ISO, which is the Inventory and Stowage Officer. I want you all to picture taking a basket of laundry and throwing it onto a bed. It just kind of falls nicely onto the bed, right? Now picture being in space and taking that basket of laundry and throwing it onto a bed, and then it all floats away. That's pretty much what the Inventory Stowage Officer has to deal with. They're in charge of stowing everything on the space station and knowing where everything is. It might seem like a menial task, but I can assure you that it's not. Even the littlest things like pens just kind of float away. And remember those vents I was talking about earlier? They have filters on them that capture things like this. So every now and then you just go like, get a pen off a vent and use it. So ISO is in charge of, whenever we have our cargo resupply vehicle, they have to have identified everything that's in the vehicle and where it's going to go. And then they have to identify everything that's already up there that can get returned back to the Earth or trashed and burned up in space. It's a very green process on the space station. So next we have OSO, the Operations Support Officer. And the best way to describe what OSO is like MacGyver. Or if you were born after 2000, it's like MacGyver. So basically, they're the ones who are in charge of helping the astronauts fix things when it's broken on the space station. The thing that they probably most commonly fix is the toilet, because you've got 6 people using like 2 toilets. And it's not like a simple toilet, because again, the no gravity thing makes it difficult, so there's lots of fans and moving parts and bags and stuff. So they actually spend a lot of time fixing toilets, fixing a lot of the life support regeneration systems, things like that. Anything that breaks on board, OSO probably knows how to fix it. You also have to have really good hair to be an OSO, as you can see. It's just like mandatory. So next we have, whoops, MacGyver again, wrong way. Next we have Pluto, which is the Plug-in Port Utilization Officer. This is the console that's literally in charge of making sure things can get plugged in to have power when they need it. Think about in your house, say you're running a hairdryer and a heater and an air conditioner for whatever reason, and a fuse blows in your house. No big deal. Go downstairs, flip the fuse, go back upstairs, resume your activities. Well, maybe not all of them, but resume what you're doing. It's a really, really bad thing when a fuse blows on the space station. So the Pluto is in charge of really just making sure if an astronaut takes their computer over here and needs to plug it in, can they plug it into that port? Will it cause a problem? What else is being powered off that line? Things like that. So it sounds kind of menial, but it's super important. Next we have 4 consoles of other stuff. The ones before were the daily stuff. This is the other stuff. We have BME, RIO, Topo, and GC. First, I'll talk about BME. BME was the answer to your question previously about the actual health of the astronauts. So they are the doctors who are on call to help with the astronauts. So They don't staff all the time. They're there usually when a crew has a medical conference or something like that. Crews have medical conferences planned so that we are always on top of the health of the crew. BME and their counterpart surgeon are some of the only other people who talk to the crew besides Capcom, because you wouldn't necessarily want like a medical emergency being translated by some dude on a console. So they're the ones in charge of making sure the crew is healthy. Then we have Rio, which is the remote interface officer. This was the console I worked when I was at Mission Control. Rio is in charge of making sure that all of the different systems and international partners work together in a nice fashion. So the way I said before, there's kind of two space stations stuck together. Everything here, this is an outdated picture, so don't look closely, but everything here in yellow belongs to the US. Everything in red belongs to the Russians. Pink is Japanese, green is European. This is the Canadian arm right there in blue. And then some other stuff. So as you can see, it is actually an international space station. You can also tell up here on the Russian side, up at the very top, there are some solar arrays up there. We also have solar arrays. So that's a really good example of how there are redundant systems on the space station. The Russians have solar arrays that can provide power. We generally use our solar arrays, but every now and then we use theirs. Sometimes, or most of the time, we give power to the Russian side so that they can do certain things. The Russian side of the spacecraft is in charge of, they have all the thrusters that actually move the spacecraft dynamically out of the way of, say, debris or something like that. So it really is an international space station, and the Rio console is in charge of coordinating all of the systems work between the international partners. We have a team of people who go out to Mission Control Moscow and sit out there for 3 months at a time. Well, they don't just sit on console for 3 months. They go live in Moscow for 3 months. And then we have a contingent of Russians who live in Houston for 3 months. So we always have kind of boots on the ground presence in the other Mission Control Center, so that if there's a problem, we can just walk down the hall and say, hey, Sergey, what's going on? And they can say nothing. And we'll go, well, then why does it look like there is? But yeah, so that was the console I worked when I was working in Mission Control. Next we have TOPO, which is the Trajectory Operations Officer. They're in charge of making sure the ISS doesn't hit any of this stuff in space. They work directly with NORAD, is that what they're called? NORAD? I don't remember, but the Air Force people who know where all this stuff is in space. They track all of the space debris, and TOPO works directly with them to make sure we don't hit anything. Because again, hitting things in space is bad. So every now and then we have to do what's called a debris avoidance maneuver, or a DAM, which I think is a very appropriate acronym for what happens when you're about to hit something. You have to move out of the way really quick. So TOPO are the people who coordinate that. They understand how much we have to move out of the way and when we have to do it, and if it will put us in the path of other things that could hit us. It's very crowded up there in space, so TOPO has quite a job. And we also have GC, which is ground control. Ground control is in charge of the actual facility of mission control. So even if it's too hot, ground control is the person who turns the air conditioner on, which never happened. It was always too cold. Ground control, as we learned from someone, in the song Ground Control to Major Tom, he erroneously says that ground control talks to Major Tom, but he doesn't. We all know that that is Capcom that talks to the astronauts. Very good. So rock and roll's not always accurate. So that's what you should take away from this talk. So just to recap a little bit, we have the flight director and Capcom here in the middle in charge of everything, talking to the astronauts. We have Kronos, ADCO, Ethos, and Spartan, who are staffed 24/7, 365. We've got Robo, ICE, VVO, and EVA, who are in charge of the dynamic operations. We've got, I had a lot of fun with the PowerPoint thing. So we have ISO, OSO, OpsPlan, and Pluto, who are in charge of the daily stuff. And then we have, like, a lot of fun with PowerPoint. And then we have BME, TOPO, GC, and Rio, who are in charge of just kind of the other random stuff. So Yes. I did, it wasn't a requirement, but it was very useful to know Russian. So when I was in high school, I studied abroad in Russia for a year, so I learned Russian pretty well. And then it was very useful to know Russian when people don't think that I know Russian when I was in Russia. So I learned a lot of fun things. Our consul worked with interpreters and translators to do the actual work. But every now and then, you know, you could overhear things. You also got a lot more respect when you could walk into their office and talk to them without a translator and say, hey, what's going on? Let's figure this out. So I used to speak Russian a lot better than I do. My dog speaks Russian a little bit, so she's really the only one I get to talk Russian to anymore.
You have told us that the flight director makes all of the real decisions. But you've told us that the Japanese have a flight director, the Russians have a flight director, and several others?
Yes.
So how do you coordinate all of those flight directors, each one which is a czar?
Well, each one isn't really a czar. So the question was, how do you coordinate the different flight directors, the different international flight directors? So you have the flight director in Houston, the flight director in Moscow, the one in Japan, in Germany, and then one in Canada, I believe. So it's not a thing that has to be coordinated in real time, really. It's more an understanding that the flight director in Houston has final say, period. However, if we're doing something that is, say, a vehicle is docking to the Russian side of the space station, something that's really a more Russian-centric operation, the flight director in Houston will most likely defer to the flight director in Russia for that. But if at that time an emergency were to occur, the flight director in Houston would assume responsibility and work the emergency. Does that kind of make sense? So it's kind of a political game, but it's one that is thought out long before it actually has to be into practice. And it's just an agreement amongst everyone. There's no law or international policy that governs this. It's more just we want the space station to work and to continue working, so we'll do whatever it takes. Is there any collusion? What do you mean by collusion?
That was a joke.
Oh, yes, I won't go into that. Next question.
I have two quick questions.
Yeah.
The first is, so is English the common language in space?
It's kind of a mixture of English and Russian. Yeah, English and Russian. All of the Russian cosmonauts speak English. Most of the American and European and everybody else astronauts speak Russian, or at least have some Russian training. The number one language that is spoken is English, so if an emergency were to occur, the dialogue would happen in English. But there are, the Russians, when they talk to Moscow Mission Control, speak in Russian. But while that's happening, there are translators on the voice loops that translate for the American flight control team. There are Russian translators in Moscow who translate all the English for the Russians. So it's primarily English and Russian. And then just depending on what other crew is up there, other things could happen in other languages.
My second question was about fixing the toilets. So is there like a guy on the ground who can fix the toilet from there when it's in space?
No.
Telling the astronauts how to fix it, or fix it like what?
Good question. So the question was about fixing toilets. Is there someone on the ground who can fix it remotely? Or are they working with the astronauts, or will it come back and get fixed? And the answer is they're working with the astronauts. So part of the glorious training of becoming an astronaut is learning how to fix a space toilet and learning how to use a space toilet, which is actually an interesting training. If you're ever an astronaut, you should ask them about it. But so the astronauts know how to do it before they get up there, but the astronauts have learned a lot of things before they go into space. So they work in conjunction with OSO to make sure that they're putting the right things in the right places and fixing them the way it needs to be fixed. I'm going to keep going because next I want to talk about, yes?
Who does the invisible planning for meals and things and determining how far in advance to put together supplies, take up there, so on?
So the question was about the invisible planning for things like meals and supplies, what you need to send up at what times, where does that take place? That all takes place in a lot of the rest of Johnson Space Center. So there's a place that develops a lot of the food that the astronauts eat. There's a whole division that's devoted just to understanding what resources are on the space station when those resources are going to deplete, when we need to refill them. That's not something that happens in real time in mission control. It just kind of, happens behind the scenes in other organizations at NASA. Yes?
How often do they have to restore the food?
How often do they have to restore the food? There's a resupply vehicle that gets sent to the space station probably at the very least once every 3 months. But it's happening more and more frequently now because we're getting more vehicles, like the SpaceX missions that are going up there, Cygnus, Blue Origin, things like that. So frequently. But it's not always just food, it's other stuff too. Yeah?
For the complement of the astronauts or cosmonauts that are up there at any time, do they consider, I mean, they all have to sort of be cross-trained, I understand that to a certain, but do we cooperate in terms of the complement that's up there at any given time that has to complement the other people that are already there? In other words, if something were to go wrong, you need the right group of people to be able to handle that at any given time, regardless of who's in the rotation or...
Sure. So the question was, to kind of distill it a little bit, what thought is given to the crew complement on the ISS and what skills they have at any given time if something were to go wrong. The best answer to that question is, if something were to go wrong, it's these people on the ground here that are going to take care of it. The astronauts may be pushing some buttons for them, may be doing some things that they have to do hands-on in space, but these people here in Houston and in Moscow and in the mission control centers are the experts. They're the ones who are going to be reacting and taking care of emergency situations. As far as the crew complement on board, I don't know exactly how the crew is selected, but I do know that there's always an equal number of Russian and non-Russian members of the space station crew, and they alternate between a Russian commander and a non-Russian commander. So not necessarily talking about the skills and such, but a little bit of how the crew is selected in general.
As a political reason?
It's a political thing, totally, yeah.
So if we asked that same question to an astronaut, would they have the same answer?
I'm sure they know exactly how they got selected.
No. Where the expertise is the guys on the ground are going to solve a problem, or the astronauts going to solve the problem?
They would absolutely answer that the guys on the grounds have the expertise for the systems. The astronauts have to know a lot of stuff when they go up into space, but they are also understand that they are not the experts of what needs to happen with the systems. They always defer to the folks in this room to take care of stuff. In general, that's the answer. Sometimes astronauts are known for being very cocky, self-assured people. So, but in general, that's the answer.
And would it be true that for the Russian portion of the space station that it's the people in Russia who would be on the ground directing?
Yes. Yeah. So it's the same thing for the Russian portion of the space station. It's the Russian flight control team that are the experts for those systems. Okay, I'm going to go through and talk about James Webb because it's happening here and very exciting. So, lots of satellites have their own mission control center, just like James Webb. I don't know if it's open to the public, but it's just right upstairs. Probably not open to the public, so don't try to go up there. Don't do it. This is a picture I took from the internet. So search JWST Mission Operations Center, and you too can look at this picture, and others like it. This is the Mission Operations Center. You can notice one thing that's really cool that I thought was awesome is all of this back here, those are windows that look out right over Wyman Park. It's really pretty. Watch the trees change and the wind and this. It's awesome. Compared to the Mission Control Center in Houston that has no windows. It's really nice here. So this is where the quiz part comes in. I'm going to relate the flight control positions on the ISS to what we're doing on James Webb. So who remembers what Spartan does?
Power.
Power, good, yeah. So they're in charge of the solar arrays and the electrical power. On James Webb, we have a similar position called EPS and TCS. Not as cool as an acronym, but still pretty cool. That stands for Electrical Power Subsystem and Thermal Control Subsystem. So it's the same sort of job that Spartan did, only on James Webb. We also have ADCO. What does ADCO do on the ISS? Attitude, good. We have something similar on James Webb called ACS and PROP. It's the attitude control system and propulsion. So again, they're in charge of the attitude of the spacecraft, but also the thrusters that keep it where we want it to be. Then we have ethos. What did ethos do? Environmental control. What do you think they do for James Webb? Nothing, because there's no people on James Webb. It doesn't have to be a livable environment, so we don't have the equivalent of an ethos. We do have Kronos. What did Kronos do?
Communications.
Communications, good. It was the communications and the video and the onboard computers. So on James Webb, we've taken all of those things and split them up into two positions. We have flight software and command and data handling, which again are the sending commands to the spacecraft and how they get handled within the spacecraft, and then the telemetry that comes back down from the spacecraft. And then communications, which is how that telemetry comes down and how those commands get up to the space station. So those are those are the subject matter experts that we have for James Webb in the control room. We also have science instruments. I had a lot of fun with PowerPoint. I'm really sorry about that. So you guys, if you've come to these lectures a lot, you probably are familiar with the science instruments on James Webb. I pretend to have familiarity with them by knowing the acronyms, such as the Near Infrared Imager and Slitless Spectrograph. Got it. The Near Infrared Camera, the Near Infrared Spectrograph, the Mid Infrared Instrument, yes, and the Fine Guidance Sensor. Those are the science instruments that are on board James Webb, and each one of those science instruments has a team of people throughout the world who are in charge of making sure the instrument is calibrated, making sure we can take the best science that we can from it, that the astronomical community knows how to use it, a whole contingent of people behind each one of those science instruments. We also have here at STSCI the people who are in charge of making sure everything from the astronauts telling us what they want to look at, all the way to sending those commands up, or sending that information up to the spacecraft, making the spacecraft point where we want it to point, taking the images, gathering that data, sending it down, and getting it back out to the astronomical community. Those people also will work here at Space Telescope in the Science and Operations Center. So we have the proposal planning subsystem, which is the suite of tools that allow the astronomers to tell us what they want to look at. We take that information, we put it on a rough schedule. We take that rough schedule and refine it a couple, I think like 10 days at a time. We refine the schedule to make sure we're taking the observations the astronauts want to look at. And then we package up that data and hand it off to get sent up to the spacecraft where those observations get executed. Hold on, let me finish this.
Astronomers, not astronauts.
Oh, I just have been talking about astronauts all night. Oh well, now I'm talking about astronomers. Well, see, now you threw me off. So the data gets sent up, the observations we want to take get sent up to the spacecraft. It takes the observations and they get sent back down to the data management subsystem, which takes all those ones and zeros that come down from space and turns them into the science that the astronomers use to do turns it into the data that the astronomers use to do all of their science. We also have the project reference database, which is basically just a database of information that each of these subsystems pull from to make sure we're all using the same information. And then we have the wavefront sensing and control subsystem that basically makes sure the spacecraft is in focus. So each one of the mirrors on James Webb can articulate on its own to make sure that the spacecraft is always in focus, so we don't run into focus issues that I hear sometimes happen on spacecraft sometimes. So these are the kind of behind the scenes things that happen here at Space Telescope to make James Webb possible. So we have the onboard systems to operate the actual spacecraft. We have the teams that operate the science instruments, and then the teams here at ST that make all of the science possible. And that's it. So, are there any more questions?
Okay, you guys got a lot of questions in during her talk, but I'm sure there are more because that's just the kind of audience you are. All right, over here.
On ISS, what is the source of the object track information that's used for the collision avoidance?
Yes, on ISS, what is the source of the object tracking information that's used for collision avoidance? We work with the Air Force. So the Air Force knows where lots and lots of stuff in space is. So the trajectory operations officer works in collection with them. And sometimes it's the Air Force calling us and saying, hey, there's a thing in the way. You should think about moving out of the way. Yeah, so the Air Force.
Why is the Air Force concerned with that?
Yes, why is the Air Force concerned with that? Because the Air Force also has a lot of satellites up there. So they want to know if any of their stuff's going to get hit. And then they just give us the information.
Very much. On the sick question again, what happens if an astronaut really gets sick, like with appendicitis or something? How do they handle that? Is there a way to bring them home?
Okay, so the question was, what happens if an astronaut gets really sick, if there's appendicitis or something? Something that's really acute, like appendicitis, I don't know for sure. If it's a really time-critical thing. It takes a finite amount of time to get the astronauts down. I think, well, I'm not sure what the fastest amount of time is, but usually when they leave the space station, they can get home they usually get home in 3 days. It can be expedited. I'm not sure how fast. But if it's something really acute, like appendicitis, I'm not actually really sure what they would do. Probably something very theatrical and heroic. But something that was less time sensitive, they can absolutely send the crew back at any time.
Did they ever send a medical doctor up as a member of the crew?
There have been medical doctors up. I know for sure for the space shuttle crews. I don't know. I would imagine there have been medical doctors that have been sent to ISS, but I don't know for a fact. You do it.
If that was the scale, if that was the scale, what would it look like? That's a friend function.
So if this was to scale, what would that look like? So this part of the James Webb is about the size of a tennis court. And the space shuttle is a lot bigger than that. So I'm not sure exactly. It would make James Webb look a lot less impressive. That's for sure. I don't know exactly the scale.
All right, so who hasn't asked a question? I think you haven't asked a question.
How many levels of redundancy is there in the Webb?
In James Webb? Oh, I was hoping it was an ISS question because I know that one. I don't know how many levels of redundancy there are in James Webb. My guess is that it's probably too fault tolerant for the systems, which means it can handle 2 things happening wrong to the same component. But I don't know that for a fact. That's my guess. Don't quote me.
I mean, with the Hubble Space Telescope, we of course have 2 sides to the electronics. We have an A side and a B side, and if the A side shorts out, we can switch over to the B side with minimal fanfare. But there were certain things where where both sides failed on the Hubble Space Telescope, and we had to repair them during servicing missions. Like, for example, the SIC and DH failed for its very first time after 18 years. And we actually delayed servicing mission 4 so that we could replace that, and so we would have redundancy in that. So, I mean, they're very careful about having a certain level of redundancy, but you can't have 10 levels of redundancy. That's overkill.
It's common practice when you make a spacecraft to at least have 1 level of redundancy. And for really important systems like your power system or your communication system, it's generally 2 or 3.
Thank you.
One thing we didn't talk about is the question of radiation hazard in terms of the equipment itself on the Webb.
The radiation hazards for the equipment on Webb itself. I did not talk about it because I don't know that much about it. And I try to only talk about things I know about. So I'm not sure.
In the very back row there.
How do political events here on the surface of the Earth affect the decision-making process for what happens on the space station?
That's a really excellent question. So the question was, how do political events here on Earth affect the decision-making process for the space station? It's interesting because the politics on Earth, the ISS is sort of immune to politics on Earth. Like right now there's a lot of, let's say, contention between Russia and the US on a political scale. But the onboard operations of the ISS are progressing normally. I know for a fact that the mission control centers are still working in tandem. I have friends who are over there right now who are perfectly happy at work and then a little wary when they go home in Moscow after work. But the ISS has been up there for quite some time, and a lot of turbulent things have happened during that time span, and it's never had an effect really on the decision-making process. The number one most important thing on the ISS is the crew. The second most important thing is the vehicle itself, and that's just a tenet that's held true regardless of who happens to be the president or what an embassy happens to be doing. So it's blissfully immune.
Does it have its own governance, or does each nation kind of manage their own capsule and then hopefully people talk to each other?
I actually think it's a really cool thing. It's an international. It truly is an international endeavor, and it couldn't be done if even just one country pulled out of the ISS, it wouldn't survive anymore. So I think it's a really cool thing.
Okay, right there.
Tell us what you're doing now. I forgot the exact job title.
Sure, I'm a systems integration and test engineer. So on that last slide that I was talking about, those are all the subsystems for the Science and Operations Center. So my team and I make sure that those subsystems are going to be fully functional by the time James Webb launches. So we are making sure everything from the software that the astronomers put in their data into to the flight operations system that actually commands the spacecraft. My team is responsible for making sure that it's going to work. Which is terrifying, but that's what we do. And we work in tandem with the people who are developing the systems to make sure that they work the way they're supposed to.
And just a note, we astronomers don't care if you call us astronauts.
Okay.
Compared to us, but you never, ever, ever call us astrologers.
I was really worried you were going to say astrologer, and I was going to lose my job. So I'm glad that I was an astronomer.
This is kind of related to the question you just asked, but what was your career path that brought you to Houston eventually and then brought you here? Like, how does someone go about that?
So my career path was, I really wanted to be an astronaut when I was a kid. I never really got over that, but then got more realistic about it. And I studied aeronautical and astronautical engineering at Purdue University. And while I was at Purdue, I got, at the time it was called a co-op, which it's kind of like a work-study program where I would alternate working one semester and then going to school another semester and then working a semester and going to school and alternating until I graduated. And I got my co-op position with NASA down in Houston. So starting my sophomore year, I would go work down in Houston every other semester, getting job skills and training and kind of seeing where I fit in the mix of everything, so that by the time I graduated, I had a full-time job waiting for me down in Houston. I was there for about 4 years and I hated Houston, so I wanted to move. And I found a job up here. I am an aerospace engineer who doesn't particularly want to work for a defense contractor, so it really limits my options. So I had been a civil servant for the government down in Houston. I found this position here literally by typing aerospace jobs state, because I just wanted to leave Houston because it's just not my favorite place. Awesome work, I loved my job. I just didn't want to be there anymore. So I found this job. I applied, they brought me up for an interview, I convinced them I vaguely know what I'm talking about, and then they hired me, so I came up here. So yeah, that's my
Okay,
path.
folks, it is 9:30, and it is always my custom that I have to cut off questions at 9:30. Irene is not in the building, so I presume there will be no observing at the Maryland Space Command Observatory tonight. Join us next month for active luminous blue variables in the Large Magellanic Cloud, and let's give Courtney a